Hey everyone, let's dive into something truly mind-bending today. Have you ever wondered how mathematicians can predict the global behavior of incredibly complex functions by looking at just one infinitesimally small point? It's like looking through a tiny keyhole and being able to perfectly draw the entire universe on the other side. Let's see how this math actually works in the real world.
So how exactly do they pull this off? It all comes down to the sheer elegance of Taylor series. It's arguably one of the most powerful ways to approximate complex functions. Today I'm going to walk you through this step by step, just like a teacher revealing the logic of how we gradually build up these mathematical models from something simple all the way to infinity.
Here is our roadmap for today. We'll start with a real-world linear approximation. Learn how to mathematically bend those straight lines. Take a look under the hood at the mechanics. Tackle errors and convergence. And finally, see how local data predicts the global universe. Let's get right into it.
Section 1. From simple to complex. Sometimes drawing a plain old straight tangent line is absolutely the best way to solve a massively complex real-world engineering problem. Let's take a practical example. Imagine a GPS satellite zooming overhead at about 4 kilometers per second. Einstein's special relativity tells us that time actually moves differently up there. Now, to calculate that exact time dilation, you normally have to deal with nasty equations full of square roots and complicated fractions. But here's the really interesting part. Engineers don't bother dividing by that messy square root. Instead, they use a simple linear approximation. Just by using a straight line, they figure out that the satellite's time is simply the ground time multiplied by 1.0000000000005. No heavy math required. Why does this work so perfectly? Because the velocity ratio is unbelievably tiny. So this straight tangent line approximation is completely sufficient. Engineers use this elegant shortcut to constantly and accurately calibrate radio transmitters on GPS satellites, saving a ton of computing power. Moving to Section 2, constructing Taylor series. We just saw a straight line work wonders, but what happens when a straight line isn't enough anymore? What if we move further from our starting point and need to approximate a function that sharply curves? So how do we mathematically bend a straight line so it perfectly matches a complex curve? The key is that to follow these complex curves, we have to systematically add higher-order polynomial terms to our equation. We start with our straight line, then add an x-squared term, then an x-cubed term, and so on. This graph brilliantly illustrates the process. See the blue straight line? It works for a tiny split second near zero. But the magic happens when we add those squared and cubed terms. Watch how the green and red curves start to beautifully bend and literally hug the true exponential function. Adding new terms visually and dramatically improves the accuracy of our curve. Section 3. Mechanics under the hood. So we know we need to add these bends, but how did mathematicians exactly find the right coefficients to make them fit? It all kicks off with the derivative. By repeatedly applying the fundamental theorem of calculus, mathematicians use step-by-step repeated integration. This natural process generates those precise polynomial terms of the Taylor series, adding a new power and a factorial in the denominator at every single step. Basically, we are locking the polynomial to the mathematical DNA of the original function at one specific point. We perfectly match its exact value, then its slope, which is the first derivative, then the rate of change of that slope, the second derivative, and we keep building it out. Section 4. Errors and convergence. Now, in serious engineering, simply saying it is approximately correct isn't good enough. We need to know exactly when our formula starts to fail. Take the classic small angle approximation for sine, where sine of theta simply equals theta. As long as you calculate strictly in radians, this linear approximation delivers 99% accuracy up to 14 degrees. But the moment you go past that, the absolute error, which is cubic by nature, becomes way too large to ignore. And different functions have totally different needs. While sine works great with a simple straight line near zero, cosine looks like a hill at that point, so a straight line is absolutely useless. Cosine demands at least a second-order, quadratic approximation right out of the gate. To strictly control these errors, we use a mathematical approach focusing on the remainder term. Using its integral form, the remainder term acts like a safety net, telling us exactly how many polynomial terms we need to stay perfectly below our desired error threshold. Let's see this convergence in action on this table. When computing the value of pi using the Taylor series for arctangent, every single new term we add systematically shrinks the error. As we build towards infinity, you can see the error percentage converging closer and closer to absolute zero. Section 5. Global behavior from a local point. This brings us to the profound historical and philosophical culmination of what Taylor series mean for modern mathematics.
Think about this. If a function is analytic, knowing its exact curvature, meaning its local derivatives, at just one single microscopic point, provides us with the complete blueprint to perfectly reconstruct and predict its global behavior all the way to infinity. The local totally describes the global. The power of this led to massive mathematical discoveries. By simply substituting an imaginary number into the Taylor series for the exponential function, mathematicians were able to prove Euler's identity. It's arguably the most elegant equation in history, beautifully uniting pi, the exponential, the imaginary unit, 0, and 1.
It leaves us with a truly fascinating thought. If local derivatives at one tiny point can flawlessly describe global infinity, what other massive secrets are hiding right now in the infinitesimally small elements of our universe? Thanks for joining me on this explainer, and keep exploring.